My name is Artem Dinaburg. I work as a security researcher for Raytheon Company, and I'm here to talk to you about a vulnerability I discovered called bit squatting. So, in these slides, I always like to start off with the problem. And the problem is that you may be compromised even when you're following the very best web security practices. So, let's go into a little more detail. Let's pretend you're a user somewhere around the world and you're browsing Facebook. When you're browsing Facebook, a lot of things get loaded in the background, such as images, JavaScript, and CSS. And sometimes they're not actually loaded from Facebook. They're loaded from a domain that's one bit away from Facebook. And Facebook isn't the only site that's vulnerable. Technically, any site is vulnerable, and the more popular a website is, the more vulnerable it is. But some of you may be out there thinking, hey, I'm running Windows 7 and latest Chrome, so this problem isn't something I should be bothered by. But you're probably wrong. This slide has actual platforms that have requested resources from me instead of from the domain they originally were going to. The problem is actually platform, operating system, and hardware agnostic. You may be thinking, hey, this is pretty interesting, so it must need a lot of skills. But you'd be wrong. It's actually extremely easy. To perform bit squatting, all you need to do is 1. Have knowledge of some simple math, 2. Be able to register domains, and 3. Properly answer DNS for them. But there's got to be some resource constraint. Like maybe you need lots of money, but actually it's extremely cheap. Like as I said, the only real requirements are domain registration and hosting. And the cost of registering a .com these days is about $8. Once again, the attack is called bit squatting. And it's called bit squatting because it's like typo squatting, but for bits. So, I'm assuming we're all familiar with typo squatting, but if not, here's a good example. Let's say you want to go to Google, which is a popular search engine, but you type an extra G, and you go to Goggle, where you can win Walmart gift cards, free iPads, but sorry, they're out of MacBook Airs. And this is not what I'm talking about. Bit squatting requires absolutely no typing. And the reason is that while humans do a lot of typing and they make a lot of mistakes, computers make a lot more DNS queries. So the graph on this slide is actually to scale. If you look at the top right corner, you see the little guy circled in red. That's the proportion of DNS requests that humans make to the proportion of DNS requests that computers make. A little bit about how I got these numbers. The 1500 comes from doing some math on the OpenDNS blog. In a blog post dated this March, they said that they had 30 billion unique DNS queries per day. If you go to their website, it says that they have 20 million users. Doing some simple mathematics leads to 1,500 DNS queries per user. Another website, visualeconomics.com, calculated that people go to 89 different domains a month. Prorated, 2 per day, that's 3. So, while bit squatters are going after the 3 domains that you type in, bit squatting goes after the 1,497 that you don't. And how can you take advantage of these 1,497 domain lookups? Computer hardware errors. Just to clarify, I'm not talking about things like bad programming, buffer overflows, or logic bugs. I'm talking about errors in the hardware that cause even perfectly written programs to misbehave. And the thing is, computers are devices made by mere mortals, and they have things like tolerances and mean times to failure. One of the potential failures that can arise is called a bit error. And in literature, these are sometimes referred to as single upset events. And this means that the electrical representation of a 1 gets transformed into a 0, or the electrical representation of a 0 gets transformed into a 1. And it's really important to notice that these bit errors happen in context. They don't happen in a void. Whenever a bit changes from a 1 to a 0 or a 0 to a 1, it happens in your, let's say, your linked lists, your trees, other data structures, maybe your login credentials, or maybe it happens in some cached HTML that happens to have a domain name. And maybe your browser will then look up that domain and fetch some JavaScript from it. So now that we've talked about bit errors, Let's go through an introduction. I don't know if you all can tell what this man is doing, but he's actually working on the ENIAC. And what he's doing is he's replacing a vacuum tube. The ENIAC was made before modern transistor technology, and it used vacuum tubes for memory storage and computation. And these vacuum tubes failed, and they failed a lot. Whenever one of these tubes would fail, the machine would either give incorrect answers, or it would stop working at all. These were the first examples of bit errors, and they've been with us for a very long time. But, we don't use vacuum tubes these days. We moved on to transistors and then integrated circuits, and they're much more reliable, and we should have never encountered any problems with ICs and random failure. Right, guys? Well, not quite. This is a RAM board from the MITS Altair 8800. The MITS Altair is actually a very famous computer. It ushered the mini-computer revolution. Microsoft's first product was Altair Basic. It helped launch the company. But we're not here to discuss that. What we're focused on is those purple chips at the top of this RAM board. Those are Intel 2107 series DRAM chips. And in 1978, two engineers from Intel, May and Woods, discovered that these chips were catastrophically failing. The problem was traced back through the supply chain, and eventually they found out that what had happened is that Intel had built a chip fab downstream from an old uranium mine. And during fabrication, these chips would be contaminated with radioactive alpha emitters. So then when this chip was running software, possibly MITS Altair Basic, an alpha particle would get emitted, it would shift some ones to zeros, and your perfectly running application would crash. They published a paper on this, and the semiconductor industry took note. They took this very seriously, and they refined manufacturing processes, and this has certainly never happened again. Right, everyone? Fast forward to 2008. This is not 2008, 2001. This is a Sun UltraSpark 2. The one in the slide is from 1997, but that's not what we're focused on. In 2001, a lot of very expensive Sun servers started randomly failing. And this server would be running, then it would crash, you would reboot it, you would do a full self-test, and it would say it's perfect, and then later it would randomly die again. And naturally, there were a lot of angry customers, and Sun started to check what the problem was, and it turned out it was radioactive contamination of their L1 and L2 cache. To make things worse, the L1 and L2 cache on the UltraSparks had no error detection, so the only time you'd realize something was wrong is when your mission-critical applications went down. But this had to be the last of it. There wouldn't really be something required, no operating system ships something to test hardware with its installation, do they? This is an Ubuntu installation. It's a direct screenshot. One of the options is test memory. Why would you ever want to test memory? Because a lot of the times your test will fail. And this is only for the only people who would actually know that it would fail is the people who decided to run that test. Think about how many people are running with bad hardware components who don't even know it. And these bit errors have security implications. And these security implications range a lot further than just random data corruption. In fact, they range from things like sandbox escapes to extracting encryption keys out of proprietary devices. So up first is a JVM sandbox escape. In 2003, Sudhakar and Apple of Princeton University published an extremely interesting paper in IEEE Security and Privacy. They had found a way to use random bit errors to escape out of the Java JVM sandbox. What they would do is they would fill memory with two Java objects and references to those objects. And when a bit error would occur, it would change one of the references to point from one object to the other. Once you had two differently typed references to the same object, you could then establish a write what where primitive, and once you write executable code to anywhere in memory, it was game over. To test their experiment, they couldn't exactly wait for a bit error to happen, so they devised the apparatus you see in this slide. That is a heat lamp attached and pointing at the RAM, and it would heat the RAM to above its critical operating temperature to where random bit errors would happen. They were able to verify their results experimentally. The next security implication is smart card piracy. there's actually an ongoing war between cable TV set-top box manufacturers and smart card pirates. Satellite signals are broadcast throughout and they're encrypted, and the way you view satellite TV is if you have the decryption key in a smart card. Well, pirates want to be able to decrypt those signals as well and sell knockoff smart cards. One of the ways in which they get to the encryption key in the smart card is they will attach to the smart card bus, and then they will induce a bit error in the smart card CPU, usually via direct electrical probing, to redirect execution to pirate code, which will then proceed to dump ROM contents before it has a chance to lock itself. Now, there's other causes of bit errors besides probing by smart card pirates and heat lamps, and I'm going to get into 4 of them. So, cause number 1 is heat. It is a physical fact that heat affects properties of electrical devices, such as conductivity and resistivity. Now, this isn't too much of a problem in desktops and maybe even laptops because they're well cooled and they're normally operated indoors. But when it comes to mobile devices, heat can be a serious issue. This is what happens when your iPhone gets too hot and eventually tells you. But did you ever wonder what happens maybe before the screen has a chance to come up in devices that don't have one, or even under what temperature it comes on anyway? So I've got a handy graph here for you guys. This is the iPhone operating temperature as taken from the Apple website, plotted against 2 climates in North America, one here in Las Vegas and one in Montreal, Canada. Right now, since it's August, we are at the top of that blue curve. If you notice, it's well above the maximum iPhone operating temperature of 95 degrees. If you've used your iPhone outside today, congratulations, you've been violating its operating requirements. So, next cause of bit errors, electrical problems. This slide is actually very apt. When I found the picture, the caption for it was that this is the backup power supply for a group of computers in rural India. We are all accustomed to always-on, very good AC power in the Western world, but this isn't true for a lot of parts. Sometimes your power is extremely unreliable, intermittent, or both, and sometimes your backups are car batteries. When you have extremely unreliable input voltage, odds are that extremely unreliable effects may propagate through your electronics. Sometimes, though, it's the electronics themselves that are faulty. Picture here is a pirate capacitor. There's actually entire websites on the internet dedicated to identifying faulty capacitors in common motherboards. Their list is a lot higher than you would think. So whenever they bid components out to the lowest bidder, sometimes they get exactly what they pay for. Capacitors also aren't the only electronic components that are pirated. There's knockoffs of all kinds of things sold on the black market, and sometimes to skimp a buck or maybe pocket the difference, people making your electronics might not use the best ones. Even if they do use the very best components, as we saw earlier in the case of the Intel DRAMs and the Sun UltraSpark, sometimes there may just be radioactive contamination somewhere during manufacturing. And speaking of radiation, that brings us back to the last, but certainly not least, cause of bit errors, and that is cosmic rays. Yes, I'm serious. And I specifically mean the intergalactic kind, not the solar kind. From all the research I've been able to do, the solar kind are generally not energetic enough to penetrate the upper atmosphere, but the intergalactic ones certainly are. Potentially, far from being a remote nuisance, there are some studies that indicate that cosmic rays are actually the #1 source of bit errors at ground level.